Hi, everybody. My name is Nathan West. I am a senior developer here on the 1Password team, on the 1Password core features team. And today I want, for some reason, to talk about atomics, as in like the memory ordering, thread interaction atomics that are so scary. All right, here's how I want to start this. There we go. Take a deep breath. It's going to be okay. Atomics have a fairly well-earned reputation of being very complicated, very easy to screw up, very difficult, very scary. A lot of that reputation is earned. There's a lot of sort of famous high-profile failures of systems because of extremely rare atomic bugs. But what I'm hoping to get across in this talk is that while they are complex, they are not beyond mortal comprehension. There's a set of rules that are well defined that you can understand, and you'll be able to read and maybe write atomic code and basically understand what's going on and make some high level estimations and not feel completely confused, completely like blown away by what is going on. All right. What are atomics? At a fundamental level, atomics are a set of rules that allow threads to safely interact with shared memory, and specifically to safely write to shared memory. We usually say we have like an atomic int, right? And then so like there are atomic operations that operate on an int. Rust uses specific atomic types. Rust has like atomic I32, an atomic bool, and so on. It does this because it uses the types to present a interface that's guaranteed to be correct no matter what. But in practice, atomics are not really any different than regular integers. It's just a different set of instructions that you use to operate on those values. When we talk about atomics, we are talking more generally about a memory model. Atomics are just one part of what we call a memory model. A memory model is a description of how your system interacts with your memory. Typically, memory models are very simple because there's a lot of competing interests at play that all want to do different things with your code and with your execution. And a memory model is sort of like a low level, well, not low level, it's a high level, highly abstract description of here's how the system will behave, implement it however you want with whatever hardware you think can make it fast. There are many memory models in existence. JVM has its own memory model. WebAssembly has its own very neat sort of slab-oriented memory model. But when we talk about the memory model, we talk about atomics, we are almost always talking specifically about the C11 memory model. This was the memory model that was launched with the release of C11 and C++11 way back in 2011. And it was basically, it's just a formal description of how atomics work that has been adopted by pretty much every language that cares to use atomics for anything. So again, the memory model is a set of rules for how threads can interact with shared memory. The memory model is primarily about describing what behaviors you could possibly see. So it's about saying like, you might see this in this order, or you might see it in that order, but you definitely won't see it in this order, right? It sort of creates a set of rules and a set of if-then conditionals that describe how things could happen throughout your code. The reason it works like this is that, like I said before, there's a lot of competing interests at play here that all want to do different things with your code, right? So there's the developers who want to write code that is ostensibly pretty easy to read, pretty fast, can basically be understood, and so on. There are compiler authors who have to figure out how does your code translate to the machine itself, right? Like basically no programming language has an idea of a register. So the compiler has to figure out how do we map your execution to registers and instructions and everything. There are optimizers who want to step in with the compiler and reorder everything. They want to transform your code and make your loops flat and get rid of branches that aren't reachable and do all kinds of crazy nonsense. There's the CPU. There's the CPU cache, right? You have the CPU cache, and if there's memory in the CPU cache, we would much rather not have to go get more memory from RAM and put it in the cache. And we would really rather not have to write stuff out to main memory from the cache. We'd love it if variables could just live in the cache forever. The CPU itself might reorder instructions. It might do branch predictions. It might do hyperthreading. Like there's so many different things that are all interacting to try to make your code as fast as possible. And so the purpose of this memory model is to say, here's what could happen. And at every layer of the system, as long as we are within the bounds of what the memory model says is allowed to happen, whoever you are, the optimizer, the CPU, the developer, can do whatever you want, and everybody else has to is promised that the behavior that comes out of it will be one that you expect. As a fun aside, before C11, before the C11 memory model, there was no such thing as standards compliant multi-threaded C or multi-threaded C++. So you talk about like P threads, you talk about like Windows threads, whatever your threading model is. None of that is standards compliant. The C standard before C11 did not have any idea of multi-threaded execution, did not have any idea that the set of things that are happening in the program might change out from under you, might have other threads be manipulating them. So it's not even accurate to say that's undefined behavior to use threads in C. It's just it's completely outside the bounds of what the standard C is capable of doing. And everybody just did it anyway, right? Everybody just sort of wrote threads anyway, and it was basically fine. But now we have a standard, and for the most part, all the real thread implementations follow this standard. All right, so that was all very abstract. Can we get a little more specific? What is the memory model? The memory model is pretty straightforward. So we have memory. Memory is a linear set of what we call memory locations. C11 does talk about bytes, which are the smallest addressable units of memory, but it ends up not being super relevant, especially for this talk. But we have memory locations, right? So like an I64, an 8-bit integer, is a single memory location. A single byte is a single memory location. Anything that is a single sort of set of byte or set of bytes that are addressable and can be manipulated with atomic operations is a memory location. We have threads. Threads perform operations on memory locations. Possibly threads will want to perform operations on the same memory location, which is what we're trying to figure out how to do correctly. The operations that threads do are either atomic or non-atomic, right? So that's just like you have like your regular old code, which is not atomic, and then you have your special atomic code, which has all these extra cool rules. And finally, the most important thing and this was actually why I had the idea to give this talk, was making this insight. I think that the number one thing that people get confused by, that this will help you get unconfused by, even though technically the spec calls memory a single set of locations, it's a little bit more accurate to say that every thread has an independent view of memory, right? So imagine all your memory. Imagine that every single thread has its own independent copy of all that memory. It's all the same pointers, but every thread is independent. And then the atomic rules describe how changes propagate between threads, right? If thread A does a write, the atomic rules describe how that write might be propagated to other threads. All right, let's talk about operations. We have our basic non-atomic operations. This is your basic code, right? You have your reads and your writes. The optimizer loves doing stuff with these. It loves sort of reordering them. It loves collapsing them. It loves trying to make them more efficient. Crucially, the memory model specifies that parallel reads are always fine. If you have several memory locations, or you have the same memory location and a bunch of threads all read from it without using atomics, that's totally fine. You are allowed to write to separate memory locations without atomics, right? So if you have one thread that writes to A and another thread that writes to B, no problems at all. Where you have problems is when you start trying to write to the same memory location. So if one thread tries to write, another thread tries to read, if either side of that interaction is non-atomic, you have now created what's called conflicts, which is undefined behavior. Anything can happen. Rust specifically goes way out of its way to make this impossible, right? Rust makes this kind of data race literally impossible, outside of like doing crazy unsafe stuff. You cannot do these not fine parallel writes. So without atomics, there's not really any way to usefully make threads interact, because the only way to soundly ensure that your writes are observable by other threads in a way that's safe is to use atomics. Let's talk about atomics. Much like regular operations, atomics are also read and writes. Atomics, much like other operations, are theoretically fully reorderable, collapsible. There's no guarantee that every single atomic that you write has to appear in the final output of your compiler. Although in practice, I think that it always will. I think the compilers tend to be very, very conservative about messing with your atomic instructions. But the spec does not require that every single atomic operation appears in your final code. Like I said, atomics allow multiple threads to operate on the same memory. And atomics always have what we call an ordering, right? So every atomic operation includes an ordering that imposes more or less rules on how that atomic operation can be ordered or reordered with other atomic operations from this thread or from other threads. Let's talk about those orderings a little bit. The first one is the easiest one. It's relaxed. A relaxed ordering imposes no requirements at all. A relaxed operation is still atomic. You can have any number of relaxed operations from any number of threads talking to the same memory location, and it works fine. But you don't get any guarantees about how a relaxed operation might interact with other operations from this thread or from other threads. Let's take a quick look at that. We're going to pop right on over here. So just as a quick example, I'm going to show off some relaxed operations. So we're going to make a counter here, and you can sort of imagine how this would be for something like, if you have like a server and you want to log how many connections you've had today. That's a great use for a relaxed operation, because it doesn't really matter what order those come in, as long as it sort of aggregates correctly. You're in the clear. So we'll have a counter. It's an atomic I32, and it starts at 0. All right, we're going to make several thousand threads. We will go ahead and actually do it like this. We will say let threads equals 0.10,000 map. We'll spawn a new thread, and this thread is going to do it's going to do some increments on this counter, right? So we're going to have several threads, and they're all just going to add one. We'll say that every thread. We'll make it an even million. So we'll do 1,000 threads. We'll each 1,000 times increment this counter. So we'll say counter dot fetch add. So the fetch part we don't care about here. The fetch part means it's going to return the old value, but we're going to atomically add something to this value. We're going to add 1 to it, and we're going to do it in a relaxed way. Cool. We will collect all these threads into a vector. We will wait for them all to finish. And we will check that. We will see if counter hit 1 million. We will print line. We will order it. We'll give it also relaxed. In this case, the joining of the threads here creates, it's going to use an ordering that we'll see in a minute that creates a guarantee that everything that these threads did has finished before we do anything else. We will run this. We're going to run it in release mode so that all the optimizations can happen and potential for silliness can happen. We'll run in release mode, and we should see that it hits 1 million. There it is. There's our 1 million. And let me actually blow this all up for everybody so you can see it a little better. There we go. All right, and there's our 1 million, right? Interestingly, we can do this incorrectly and show how this can go bad, right? So this is an atomic increment operation, but what we can do instead, we can do something silly. We can say let value equals counter.load relaxed. Let value equals value plus 1 and counter dot store value. All right. So what we've done here is we have now split it into 2 atomic operations. We are guaranteed that both of these atomics will be, like I say, atomic, but there's no guarantee that this entire block here is atomic, right? It could very easily be the case that 2 threads will simultaneously load a 10. They will both compute that the next value is 11, and they will both try to store an 11. And one of them will succeed, and the other one will succeed, and we'll end up with an 11 instead of a 12. And if we run this, hopefully we'll see a number a little bit less than 1 million. There it is. So 970,000, right? So we can see that our threads have raced against each other and done something incorrect here. Okay, so that's our relaxed ordering, right? It just does a simple atomic operation that has really not any guarantees about ordering. let's look at what can go wrong with relaxed orderings, right? Here's some of the problems we can have. We're gonna be looking at a lot of atomic problems and a lot of sort of surprising things that can go wrong. And we're gonna be doing this in the curse zone. This is where all of the cursed code is gonna live. Let's take a look at our first one. Here's a simple example. Oops. Here's a simple example. We have one thread. It wants to store the 10 into an X. It wants to store 20 into Y. For all these examples, we're going to assume that every variable starts at 0, and then we change it away from 0. So we have one thread that stores 10 and 20. We have another thread that loads X and Y into A and B. Let's take a look at what can happen here. So thread 2 can go first, right? Thread 2 just runs before thread 1. It loads a pair of zeros. Fine, that's sort of easy. It might go in the middle. It might go here. It might load a 10 and then a 0, right? It might get this 10 from X, but not this 20 from Y. It might go at the end, and we have a 10 and a 20, right? And of course, you can also see like the one load could happen here, another load could happen down here, but it sort of ends up being the same thing. But another funny thing we could see is 0 and 20. We could see this 20, but not this 0. This is where the ordering stuff comes into play, right? Relaxed provides no ordering guarantees between different operations. There is no guarantee that this 20 has to be visible after this 10. We could very easily see a 20 before 10 if the optimizer for some reason chose to swap them around, or if like maybe the 20 landed in the CPU cache before the 10 did. There's all kinds of reasons this could happen. And the point that I really want to get across here is that this is allowed to happen. And there's tons of reasons why it could happen. And a lot of articles and blogs and so on will sort of diverge into talking about CPU fences and caches and everything. And I really want to emphasize that what's important, especially as an author, unless you're writing like super high performance multi-threaded code for a single platform, what's important is the model. The model describes what you can see, and you want to make sure that all the possible behaviors that your code might exhibit are correct. And once you have that, now you can rely on the optimizer or the CPU or whatever to do correct transformations on your code, and it'll never be buggy, it'll never leak memory or do whatever bad things it might do. All right. Unfortunately, though, it does get worse. Let's bring in a third thread. So maybe this thread wants to load as well, right? So maybe this thread runs around the same time a thread 2 does. These operations were swapped. We see a 0 and a 20. All right, well, that's okay. Maybe this thread runs a little later. Maybe this thread sees the 10 and the 20, and this thread doesn't see the 10, right? So we stored a 20, we stored a 10. The thread 2 ran in the middle there. Thread 3 ran at the end. All right, that's no problem. This is also possible. This is going to be a common theme here. When it comes to these atomics, time is a lie. You need to set aside the idea that things happen in some particular order, or that there is any sort of consistent time between any of the things that are happening here. What we are describing is possible observable orderings. I mentioned earlier that every thread has an essentially independent view of memory. This is what we're seeing here. This thread performed these stores in some order. Thread 2 saw the Y, but not the X. Thread 3 saw the X, but not the Y. That's just how it goes sometimes. Now, what's annoying about this is that it's actually very, very difficult to produce results like this in practice. It's very difficult, and I couldn't do it. It's very difficult to write code that does things like this. And when it happens in production, usually it happens, once a year. And so this is what makes atomic code such a pain to debug and such a risk if you're doing unsafe things around the atomics and relying on atomics to uphold your safety guarantees. There's a lot of weird stuff, and a lot of your intuitions about cause and effect and time passing and so on just don't really hold up. All right. This problem, though, is surmountable. We're going to start imposing some ordering rules on our threads. We're going to start with release and acquire. I always really hated release and acquire. I thought that they were very, very, very confusingly named. And there's a lot of stuff like, acquire is like acquiring a mutex, and release is like releasing a mutex. And that I always found that very, very useless. That doesn't really, I never found that created an understanding of what was going on. It turns out, though, that there is a simple way to describe what's going on that really did drive it home for me. So release and acquire operations always go together. There's always a release operation only imposes requirements on a neighboring acquire operation. Specifically, a thread can release its rights, its operations, to be acquired by another thread, right? A thread A can acquire stuff that was released by thread B. That's the key intuition here. Specifically, what that means is that when you do a release write, that thread has now guaranteed that all of the writes that it did before that are available to any threads that acquire that particular write, right? So if I do a release write to X and some other thread acquires X and it gets the new, if I store true to X for done, and another thread acquires that true for X, that thread, it's now guaranteed that that thread has acquired at least everything that the first thread did. Okay. So this is sort of the basic, this is where like a lot of like your spin locks can come from. We'll see in a minute. Actually, I'm just going to write a quick little mutex, and you'll see how it can work. But that's the key thing here. I find that it helps to almost always I see it described as acquire/release, and I like saying release/acquire because that's the order that things happen. Thread A releases memory to be acquired, or releases operations to be acquired by thread B. Release acquire imposes some reordering requirements. When you have written a release write operation, you are not allowed to observe that any operations before that release got reordered to after it, right? So if I store X equals 1 and I release store Y equals 2, that X equals 1 cannot appear after the Y equals 2. This is going to solve the problem that we saw a minute ago. Similarly, on the acquire side, any reads that you do cannot be, or any operations you do, but specifically reads, cannot be ordered to before the acquire, right? If you have acquired all the writes from another thread, all the reads you do after that acquire can't happen before the acquire. The acquire is the moment when you got those results, and it's sort of guaranteed that the operations you perform are going to benefit from those results. Let's dive into this a little bit more though, because this does it is easy to start sort of applying your intuitions about how time works in ways that don't really work. When you do a release write, it's not really, you can't really meaningfully say that it happened, that we have done a release write and now the threads can see it. That's not really how the model works. The model is really defined in terms of if-then operations, right? If I release, so if I have some variable that's false, and I'll write this out in a second, but I kind of want to just give a colloquial explanation. If I have a variable that's false and I release a true, other threads can still see the false, maybe. Like they still might read a false, because we saw earlier that time is an illusion and threads have independent views of memory. The only guarantee that I have is that if a thread sees the true, then it has successfully acquired what was released by the original thread, and it can see all the other operations, right? You might still see the false, and if you see the false, then you have no idea what's going on. But only if you see the true, not when you see the true, but if you see the true, then you know that the acquire has completed from the associated release. Like I say, release and acquire are paired up. You can't acquire a relaxed operation. You can't release to a relaxed operation. You acquire things that have been released. There is another ordering that we see in C++ we don't see in Rust called consume. We don't talk about consume because it turns out that it's extremely hard to implement correctly and nobody has done it successfully, and it's an extremely convoluted dependency tracking thing that basically everybody ignores, and Rust explicitly ignored. So we're not going to worry about that. Release releases all writes that thread did, and when you acquire that write, you have acquired all the writes, no matter what they were to. Everything that snapshot of that thread's operations, and maybe stuff afterwards, but at least up to that release has been acquired. All right, let's write something for that real quick. Let's just show that off a little bit. We are going to write a quick and simple and correct mutex. Once I can figure out where to put my keyboard, maybe over here. Let's make this a little smaller. There we go. Actually, I'll just do this. We'll make this a little bigger. We will close this. There we go. All right. We're going to go ahead and make a spintex, aka a spin lonky mutex. Spintex. It's got something in it. You might recall from my previous talk that I gave that when we're talking about interior mutability, when we're talking about mutating stuff through shared references, which mutexes do, we are required to use this thing called an unsafe cell. That's a requirement that Rust imposes because Rust will govern the optimizer appropriately, where Rust really will assume that stuff behind a shared reference is immutable unless it is inside of an unsafe cell. So we have to use one of those here. And we'll say, is it locked? That's an atomic bool. Great. Let's go ahead and put some simple methods on it. We'll make a new unsafe cell. And we will make we'll say that it starts unlocked. This is an atomic bool, new false. Cool. And let's lock it. We're not going to worry about try lock or timeouts or anything like that. We're just going to just do this basic blocking lock operation. We'll make a guard object, just like our mutex has, struct spintex guard. Spintex guard borrows the underlying object. So it's just got a is a reference to our spintex. Cool. Let's go ahead and make one of these. All right, so here's where our atomics come into play. So we want to create a spintex guard, and actually let's go ahead and put some basic operations on this too, so we can see how it's going to be used. We're going to implement deref for it, so a spintex guard can be just derefed into whatever's inside of it. Impl deref t for spintex guard t. We're going to give us a t, and we know that we are locked, which means that we know that it's safe to pull a value out of this unsafe cell. So we are going to do self.spintex.value.get. Get is the interface of an unsafe cell. It returns a pointer, which is unsafe to do stuff with, but we are guaranteed because of our lock that we're okay. So we're going to go ahead and dereference that guy. We are going to return one of these, spintex guard borrowing self. Cool. All right, so we need to block and return only if we can lock the mutex. So we're going to do an atomic operation. We're going to try to store true into this variable, but only proceed if it was previously unlocked. So we're going to say self.locked.swap. So we're going to swap true. Swap is going to return whatever it was before. So if this returns false, then we are clear to go, which means that as long as it returns true, we want to keep looping here. So we're going to go ahead and actually just put a while loop here. Cool. Now we need an ordering. Okay. So let's think about this. We need to be sure that when we acquire the lock, we have acquired any changes that other threads, so if another thread did a bunch of work on this value and then unlocked this lock, released the lock, we want to make sure that we can see all those changes, right? We need to be guaranteed that we're not going to get interleaved into the work that the first thread was doing. On the other hand, so we do need to at least do an acquire here. On the other hand, swap is a read and a write, right? So swap stores a true and reads the old value. But it isn't really necessary to release the true, right? At this point, this spintex has not done any work. This thread doesn't have any work that it needs other threads to be able to see, right? So it's not necessary to put a release ordering on the true, right? That release ordering is going to say, at the moment we lock this mutex, make sure everything that happened before that gets released. Well, things that happen before you lock a mutex, sort of by definition, are not interesting. They're not critical, which means that we can do an acquire here. And so this will be the equivalent of acquiring the old variable, but only storing the new one in a relaxed way. That being said, it is still atomic. We are sort of guaranteed that if many threads perform this operation, only one of them is going to get a false, because all of these swap operations are atomic and they'll exist in some order. and whatever one goes next is going to see the true that we just stored there. Yes, it's interesting. I'll talk about that right now. I saw this question here about sequential CST, sequential consistency. We'll get to that in a minute, but I'll give you a spoiler here. It turns out that you very, very rarely need sequential consistency. It adds a couple extra rules on top of acquire release that, I'll just say it. I was not able to come up with an example of a problem that I would need specifically sequential consistency to solve, that acquire release would not be sufficient for. But we'll see that in a minute. All right, let's finish writing this. So while we do this, we do want to go ahead and do a thread yield here. We want to make sure that if this mutex is locked, we don't want to keep spinning forever. We want to give other threads the opportunity to make progress. We'll go ahead and throw a yield right here. All right. Now at this point, we know that this returned false. So it was unlocked. Now it's locked. Yes, we'll talk about ARM in a second here, Ivan. Let's go ahead and return something. Let's go ahead and return a spin text guard with our spin text being self. Great. Finally, let's go ahead and throw a couple more methods on this thing. Let's make sure that we can get a mutable reference to it. That's sort of the whole point, right? We want to be able to lock it so that we can do mutable things to it, even though multiple threads have a reference to this guard. We will go ahead and say deref mute for spin text guard. We will do the same thing, unsafely, mutably reference the pointer self.spintext.value.get. Cool. And finally, we got to unlock, right? We have our guard. Eventually, the guard wants to be done. When the guard is dropped, the mutex is unlocked. So we will go ahead and throw a drop on this. Drop for spintext guard T. So we want to drop it. We need to unlock. All right. So now it's the same thing in reverse. So where previously when we stored a true here, we said, well, nothing before this true is really important, so we can do that in a relaxed way. That is not true here. After we're done with this lock, we have done a lot of very interesting things to this value here, and we need to guarantee that those values are propagated to other threads. If another thread acquires that this is false, it needs to have also acquired all the changes that we made to this value. That's what our release is. We're going to say self.spintext.locked.store true with release ordering. Cool. Let's go ahead and throw this lifetime in here that we forgot about. Let's go ahead and get rid of all this because we're going to do something different. Great. The last thing we need to do here is unsafe cell is going to impose a lot of thread unsafe things. It's going to say this is not send and not sync, which kind of makes sense. But because of what we just wrote, we know that what we wrote here is safe to use in other threads. So we can go ahead and say, if T is send, so is our spintex. If T is sync, so is our spintex. We can say the same thing on the guard. And in fact, we can actually do a little better on the guard. Normally mutex guards are never send because a real mutex has to be guaranteed the same thread unlocked it that locked it, because implementations require that. But this is just a boring all-atomic. So we can actually safely do this anyway. We can put this here, we can put this here. We can put our lifetime in place. Cool. Shouldn't the guards drop store false in the drop? That sounds right. Yeah, let's make it unlocked. That's a good catch. Thank you. All right, great. All right, let's go ahead and do it. We're going to go ahead and make a value. It's going to be a regular all. We'll make it a regular integer, even though we can do atomics with integers. We want to show off the mutable stuff. So we're going to say let value equals arc new spintext. Actually, let's go ahead and import arc. New. Wow, did it really make my menu that small? Weird. Arc new spintext new. Let's make it 0. Great. All right, let's make 10,000 threads. Why not? We have a lot of memory these days. We'll say 4. We'll do our thing before, so we'll say 0.10,000 dot map. Actually, we'll do 1,000. Oh no, we'll do 10,000. 10,000 is good. We will go ahead and spawn a thread. Actually, we'll have to do some cloning here. So we want to get let value equals value dot clone to clone the arc. We will spawn a thread. So let's spawn. Let's move this arc into the thread. Cool. Let's lock it. Let lock equals value dot lock. Let's increment it. Lock plus equals 1. And just to sort of make it spin for a while, we'll actually go ahead and throw a sleep in here too. We'll go ahead and say thread sleep. And we're going to sleep for, do some mental math here. We will sleep for 100 microseconds. And we will do that because 100 microseconds 10,000 times should be about 1 second. And so we should see that this sleeps for about a second. While this is asleep, all of the other threads will be spinning on this lock. We'll go ahead and actually put a drop lock here just to ensure that it gets dropped at the end. We will put a semicolon here. Actually, no, we won't. We will dot collect vec. Cool. Let's make this mutable. Great. All right. So we have all these operations. We will go ahead and finish all the threads. Threads dot into iter dot for each thread dot join dot unwrap. Hopefully none of these threads panic. Great. And we should be able to see. We'll go ahead and lock it locally. Let lock equals value dot lock. And we should see that this is 10,000. We should also see that my computer gets very, very, very hot as it saturates every single core that I have to throw at it with a spin lock. We are going to print lock. Cool. We will print star lock. Why not? Great. All right. Let's see what happens here. Let's go ahead and try to run this. I'll build it. Should take about a second or more. Oh boy, there it is. Yeah, there was some contention there, which is probably why it took a little longer than a second. But there's our 10,000, right? We have a lock. Now it's possible this would have worked anyway. And what we can do, I'm gonna calm this down a little bit. We're gonna drop this down to just 100 threads. There's a tool you can use called Miri. Miri is sort of a Rust interpreter that checks for undefined behavior. It sort of simulates all of Rust's memory and all the operations you might do. And we're not using atomics here for the value, at least, right? This where is it? This value is not an atomic that we put in the spintex, which means that if our lock didn't work and if several threads were able to mutate this at the same time, Miri should start screaming at us about it. Let's see what happens after it rebuilds. It's also possible that Miri won't say anything because Miri can take a while to run sometimes. Oops. What do we said about here? Oh yeah, we can't sleep. We can't sleep in Miri. That's fine. So we'll go ahead and get rid of this sleep. And let's try that again. Hopefully we'll see that this works okay. There it is. There's our 100 for our 100 threads. Miri didn't have anything to complain about. Looks like our lock was okay. Cool. All right, that's acquire release. Now, guess what though? It's time to return to our favorite place, the curse zone. This could be a little bit less cursed because acquire release provides more guarantees. Recall earlier that I said that when you do a release, you are releasing all the work you just did to other threads, which means that it is guaranteed that anything that happened before the release won't get reordered to after release, right? So do critical work here won't get reordered to after this too, right? So suppose like progress is a progress bar, right? 1, 2, 3, we're doing some work, we're doing some more work, we're updating our progress as we go along. It is possible that it's not possible that this will get reordered to after the 2 or that either of these will get reordered to after the 3. Now, that's only one direction though. It could go the other way, hypothetically. There is no requirement that it can't get reordered the other way. And what's interesting about this is that this is not inconsistent with the rules of the ordering. It's not it isn't required that when you do an acquire, you are seeing precisely everything that happened before this. It's only that you're going to see at least what happened before this, right? So if it happened that the compiler put everything in this order, but your thread just didn't run for a while, the scheduler said your thread had to go to sleep for a while, you might not even see anything until all the way down here. Which means that if the optimizer chooses to reorder this stuff like this, that's not inconsistent with anything that you could see, right? That's our memory model. Things that you could see, behaviors that you could observe. And the optimizer working in those constraints to provoke maybe things you don't expect, but things that are allowed. We can keep going like this. We can put all these down here, and we can do one more cool thing, right? What we now have here is a set of 3 stores in a row. Well, clearly these are kind of redundant, right? And like I just said, there's no guarantee that this moment in time where my mouse is between the 1 and 2 exists, because time is an illusion, right? What I'm about to show, I am pretty sure no compiler does. I found a lot of really interesting threads on mailing lists and everything, explaining why compilers really don't do this. It's just too hard to do correctly in general. But in theory, an optimizer could do the same thing that a regular old plain optimizer does and say, well, those writes are redundant, let's get rid of them, right? So it could just say, do some more work, then store a 3. That is a valid optimization of this code. And it is not inconsistent with any of the rules of what you could observe. There's no requirement that you have to maybe be able to see the 1 if you're fast enough. The only requirement is that if you see the 1, if you see the 2, do critical work has finished. If you see the 3, do more work has also finished. And this code that I've just written is consistent with that, right? You never see the 2, well, whatever. But you see the 3, so all your guarantees are still held up. Like I say, this probably won't happen in practice. Compilers are very, very, very cautious around screwing with atomic operations in this way, but it is valid. Let's do some more curse stuff. Let's look at our triple threads again. So when I said earlier that release creates a certain order where release, everything that happened before the release, to the extent that before is a real thing, is released to any thread that acquires that write. Now, that's only the one thread, though. If you have several different threads that all do a release write to different variables, there's no guarantee, there's no requirement about the order between these different variables, right? This release means that everything that thread 1 did is available. This release means everything that thread 2 did is available, and this release, everything that thread 3 did is available. But we can do our time travel nonsense again, right? So after we do some stores here, we can load Y and load Z. Notice that Y is 2 and Z is 0. All right, so maybe Y happened first. And then we can load X and Z. We can see that X is 0, Z is 3. All right, maybe Z happened first. And then we can see, oh wait, X happened first too. They all happened first. And this is sort of this is just a weird thing that can happen. Does the reordering curse of each release is releasing data that is dependent? Yeah. So I'll read this question so I can hear it. Does the release ordering curse go away if each release is releasing data that is definitively the result of the work steps? It's specifically, the curse goes away because you are releasing data that this thread did. Release is a promise about things that this thread did. When this thread does a release write, everything that this thread did before doing that is released. Now, if that thread's work depended on stuff that it acquired from other threads, the same thing does start to apply transitively, right? Where it's sort of guaranteed that if thread 2 had to do a bunch of work based on thread 1's work and then releases it, there isn't any possible ordering where thread 1's work is not available to thread 3. In theory. Yeah. So it's interesting what you're saying this about this dependency thing. What you're describing here, Savani, so I'll read this question again. I understand the devil's in the details of proving to the compiler that the release is dependent on the work. What you're describing is actually precisely consume ordering. Consume ordering is about dependency. When you do a consume read, I think, it is now said that, well, everything that was dependent on that acquire write is captured. Defining a dependency in that way is enormously difficult, and as far as I know, no compilers actually do it. Turns out that it's very easy to say everything this thread did, regardless of whether it's an observable dependency, is part of the release operation, and we're just going to release everything that happened is going to get released, which turns out to be fine. That turns out to be what you need in general. All right. this last cursed example is sort of contrived. You would never really write code like this, but I wrote it because I need to talk about the last ordering, the one that everybody uses by default because it's the safest, which is sequentially consistent. So this is the one you see get thrown around just because, well, I'm not really sure to understand atomics. So I know that sequentially consistent provides the most guarantees, so I'm just going to use them. Sequentially consistent means the same thing as acquire release. If you do a sequentially consistent write, it acquires writes, or if you do a sequentially consistent write, it releases previous writes. If you do a consistent read, it consumes reads. The other guarantee you get though, so previously we saw this sort of time travel example. The other thing you get though is that all threads observe all sequentially consistent operations in the same order, no matter what. If we revisit our time travel example, this is now impossible, right? We've changed our stores here to be sequentially consistent. Thread 1 observes that Y happens before Z. Thread 2 observes that that Z happens before X, which means that X must happen last. Therefore, thread 3 can't possibly observe that X happens before anything else, right? If thread 3 observes X equals 1, it's also going to observe Y equals 2 and Z equals 3. That's the extra guarantee you get, is this sort of global ordering. Now, it turns out that that sort of global ordering is actually very rarely what you want, because usually the things you're trying to order are confined to a single thread, like a thread does a bunch of work, and then it wants to make that work available to other threads. And pretty much always acquire release or release acquire is sufficient to get that across. All right. Let's do a quick recap. I know that was a lot of things and much less code than I usually write, but like I say, it's very hard to write code examples for this stuff because it's very hard to provoke the problems you might see. Just to recap, we have a memory model. A memory model is a description of is an abstract description of possible observable outcomes for a set of parallel operations that threads do. It describes what could happen. Atomics are sort of the primitive operations that are defined under the memory model. And they have rules about how these atomics can be reordered relative to each other. And again, this last one is technically not part of the spec, but it's so useful for creating an intuitive understanding of this. Every thread has an independent view of what's going on. They might observe things in different order. They might observe things in seemingly inconsistent orders. Every thread has an independent view, and it may or may not see things that other threads have done in a way that is independent of what other threads are also seeing, subject to the acquire release rules that we just talked about. We have our non-atomic operations. Like I say, it is always unsound to do a non-atomic operation when a write is involved. So if you do a non-atomic read and an atomic write, that's bad. If you do a non-atomic write and an atomic read, that's bad, right? But if you do a bunch of non-atomic and atomic reads together, that's fine, and so on. Relaxed imposes no requirements. Release acquire. A thread releases memory to be acquired by another thread by doing a release write and an acquire read. And sequentially consistent, same thing, but also every sequentially consistent operation happens in the same order on every thread. All right, now it's very easy to get in the weeds on this stuff, and it's very easy to sort of like as you start to grasp it, your brain gets a little too big, and you start to think about things that don't make sense even under this model. So we're going to return to Earth a little bit, and I'm just going to point out some things that I got wrong very frequently that these are easy to forget. All right, first of all, we were talking about multiple threads here. All of the old rules about optimizers reordering operations and whether or not those transformations are observable, that's just multi-threaded stuff. All the old requirements about single-threaded observability still hold, right? This code here that does a series of increments and then a load and then a series of decrements, if there's no other threads, we're always going to see a 3 here. There's no there's no world, like even if theoretically it does reorder these operations, there's no way that this should be print A. Oops. There's no way that this print shows anything other than 3 if there's no other threads involved, right? And maybe the optimizer does some transformations, but we still have to see a 3 here, right? It's all the weird nonsense only really starts happening when there's other threads involved. So we talked a lot about acquire and release and how when things have a total ordering. Atomic operations on a single variable always have a total ordering. If you're only ever working with a single variable and you're not working with anything else, so like the counter we did on the first example where we just incremented a whole bunch, that's a good example. The lock is a bad example because the lock, we have the critical section and also the lock, 2 variables. We need to do more. If you have just a single variable that you're dealing with, relax is probably okay, because it's guaranteed that every relaxed operation will have a consistent order on the same memory location that'll be observed by all threads. So in this example, right, we swap a 1 and we swap a 2. These might happen in different orders, but there's no way that both of these threads print a 0. There's no way that, like, even though the threads have independent views of memory, there's still no way that both of these threads decide to use their 0, right? These operations are atomic. If thread 1 goes first, it stores the 1, thread 2 is going to see that 1, not see that 0. And finally, this is all completely insane. A lot of what I showed and a lot of the curse stuff that I showed is purely theoretical. Compilers are very cautious around atomic operations, and they are not going to be doing a bunch of nonsense. In addition, like I said, it's all if this. Excuse me. It's all if then stuff. If you see this, then you could see this. But remember that the computer is not trying to confuse you on purpose. Everything will propagate eventually. If you store, if you say x equals y plus 1, eventually all the threads are going to see that x. The memory model doesn't provide any guarantees about when, because we don't have time. Time's an illusion. But it is going to happen eventually in practice, right? It is going to, probably within a few microseconds, that's going to get propagated to all your other threads. All right, I have one last thing to show here, but I'm going to go ahead and review the Slack thread and see if there's any questions I missed. Oh, somebody asked about ARM. Yeah. So that's actually a really good question. So one of the things that makes this especially hard is that CPUs have their own rules about what things are atomic and how that all works. Those rules have to be consistent with the model, but otherwise they can do whatever they want. x86, with a few rare exceptions, tends to impose sequentially consistent orderings for everything, everywhere. Every store, every load, it's all sequentially consistent, and x86 guarantees that. And so it's just gonna work, right? Like, you can always upgrade any of these orderings to a stronger ordering without you'll see the same, you'll see a smaller set of possible behaviors that's still consistent with the weaker ordering. This created a very funny problem, especially when the new Macs came out, because ARM provides much weaker guarantees. ARM does allow for weakly ordered operations and out of order observations between threads and stuff like that. And it turns out that there was a fair amount of incorrectly written atomic code out there that had only ever been run on x86 that just worked correctly because of the extra safety that x86 imposed, that once ported to ARM stopped working. This is why I try not to get bogged down in stuff about like fences and CPU atomics and CPU consistency. I really want to focus on the model. The model describes what can happen. If your code is consistent with the model, it'll be consistent with whatever, modulo bugs in the compiler or whatever. It'll be consistent with whatever things the compiler and so on do with it. All right. Are there any last questions? We have about a minute left, and there's still one more thing I want to show, but are there any last minute questions before I do this last thing? No? All right. Guess what? We are returning for the last time to the curse zone. This is the ultimate curse zone. I stumbled upon this example when I was doing research for this talk, and I basically died and came back. But my soul left my body. All right. Now, recall that I said earlier that in all my examples, every variable starts at 0. So we have here, if we load a 1 from x, store 1 to y. If we load a 1 from y, store 1 to x. How on earth could this possibly result in anything other than nothing happening? It turns out that under the formal rules, it is possible for these stores to happen. It is possible theoretically for it to decide that we have loaded a 1, store the 1. Okay, we got a 1 here, store the 1. Oh, this 1 that we stored here back in time now fulfills this requirement. The way this can happen in practice is with a branch predictor, right? If we have a branch predictor in our CPU and the CPU wants to keep on executing code before it's worked out if it actually should or not, it might predict that this is true, do this, store the 1, and then when the branch predictor goes back to work out what happened, oh, it's 1, we're fine, great, let's move on. Probably this won't ever happen after Spectre, because Spectre was all about exploiting that kind of issue to leak secure memory. And I will give you $100 if you ever see this happen in the real world. But theoretically, this could happen. This is where it gets bad. All right, that's what I got. Thanks so much, everybody. I'll take one final round of questions. I also want to shout out Mara Boss, aka @Mouse on Twitter. She's the leader of the Rust library team, and this talk would not have happened without her. She, I was basically making some posts about how inadequate I found most introductory material on atomics, and she reached out to me in the DMs, and we chatted for hours and hours and hours and hours over the past weeks. And she got me up to speed. It was amazing. And I just have to give her a shout out. Any last minute questions here? I know we're right at time. No. All right. Thanks very much, everybody. I hope you got something out of that. Feel free to come to me with any other questions you might have. There are one last little sentence here. There's a pair of tools. One's called Miri. We saw that. Another one's called Loom, which is made by the Tokyo people. Loom. Loom is a tool that simulates this work, right? Loom is a tool that you can use in Tokyo, and it will go out of its way to try to simulate different orderings and try to create bugs in your multi-threaded code. It's very, very, very cool, and you should check it out if you're actually doing any of this stuff. All right. Thanks so much, everybody. Have a good rest of your Tuesday.